Let us now explore how real-world networks can be represented with graphs. Every time you check a friend's profile, every time Google Maps finds you a route, every time Netflix recommends a show, you're interacting with a graph. A graph is just a collection of things and the connections between them. But here's the thing. How you explore that graph changes everything. Do you spread outward like ripples in water, guaranteeing the shortest path? Or do you dive deep, exploring one direction fully before backtracking? That choice, BFS versus DFS, unlocks solutions to some of the most important problems in computer science. Finding connections, detecting cycles, building recommendation engines, even tracking disease spread. By the end of this video, you'll understand what graphs are, how they represent real networks, and the two fundamental ways computers explore them. Let's start with something you already know. Your social network. Here, we see individual nodes representing entities, like people in a social network or intersections on a map. These edges are the connections between nodes, showing relationships or pathways. Building this simple network demonstrates how complex relationships can be represented as connected nodes, forming the foundation for graph exploration. Now, let's explore two fundamental strategies for navigating these graphs. Breadth-first search, or BFS, and depth-first search, or DFS. Each offers a unique approach to traversing the network. Breadth-first search starts at a designated node, like Alice, and systematically explores all its direct neighbors before moving to the next level of neighbors. BFS uses a queue data structure to manage which nodes to visit next, ensuring a level-by-level exploration. Nodes are added to the back and removed from the front. This breadth-first approach guarantees that the first time you discover a node, you found the shortest path to it from your starting point. The distance labels indicate the minimum number of edges required to reach each node from Alice, a direct result of BFS's systematic layer-by-layer traversal. In contrast, depth-first search, or DFS, explores as far as possible along each branch before backtracking. It's like navigating a maze, always trying to go deeper. DFS uses a stack data structure to keep track of the path it's currently exploring. Nodes are pushed onto the stack as you go deeper and popped when you backtrack. When DFS reaches a dead end or a node with no unvisited neighbors, it backtracks to the most recently visited node that still has unexplored paths. This depth-first exploration is excellent for tasks like detecting cycles in a graph or finding all possible paths, even if they aren't the shortest. The discovery order labels show the sequence in which each node was first visited during the depth-first traversal, reflecting its systematic yet deep exploration. As you can see, even on the exact same graph, BFS and DFS yield vastly different results in terms of exploration order and the information they prioritize, such as shortest paths versus a complete traversal of a branch. Understanding these distinct exploration patterns is key to choosing the right algorithm for your specific problem, whether it's optimizing routes or mapping complex dependencies. Ultimately, graphs provide a powerful framework for modeling interconnected systems, and BFS and DFS are your fundamental tools for navigating and understanding them. So what exactly is a graph? It's simpler than you think. A graph is just a collection of nodes, things like people, cities, or web pages, and edges, which are the connections between them. Think of nodes as dots and edges as lines. That's it. But here's the key decision. How do you store the structure in memory? You have two main choices. Let's see both in action. The first is an adjacency list. Imagine a phone book where each person lists their friends. The second is an adjacency matrix, a big checklist table where rows and columns represent people, and you mark a cell if two people are connected. Adjacency lists are fast and space efficient when you have few connections. This method's efficiency is order of degree, because it depends on how many connections a node has. Adjacency matrices are simple and instant for checking if two nodes are connected, but they waste space if most cells are empty. Their efficiency is order of 1, representing a direct lookup. For space efficiency, adjacency lists often win. They store only real connections, while adjacency matrices allocate space for every possible pair of nodes. Now let's explore the graph. There are two fundamental ways to do this: breadth, first search, and depth. First search. Breadth. First search explores level by level, like ripples spreading outward from a stone dropped in water. It uses a queue, a first in, first out structure, to keep track of which nodes to visit next. This guarantees you'll find the shortest path in an unweighted graph. Depth. First search, on the other hand, dives deep down one path as far as possible before backtracking. It uses a stack, a last in, first out structure, or recursion. Depth. First search doesn't find the shortest path, but it's perfect for detecting cycles or exploring all possibilities. Let's watch both algorithms run on the same graph, side by side, so you can see exactly how they differ. Pay attention to the order in which nodes are discovered and the data structures driving each algorithm. Depth. First search begins at Alice, then immediately follows one path deeper into the graph. Each newly discovered node is pushed onto the stack, creating a trail that the algorithm can later retrace. Breadth. First search continues expanding outward level by level. David is discovered only after every node one step away from Alice has already been explored. The search now reaches David. Since there are no unexplored neighbors, the algorithm backtracks by popping David from the stack and returning to the previous node. Back at Bob, depth first search explores the remaining branch through Carol. Once every reachable node has been visited, the stack gradually unwinds until the traversal is complete. This side-by-side comparison highlights a crucial difference. While both algorithms explore the entire graph, their traversal order and the paths they emphasize are distinct, leading to different insights and applications. Notice how breadth first search, by prioritizing layers, naturally identifies the shortest path from the start node. Conversely, depth first search prioritizes diving deep, making it adept at exploring extensive branches and identifying structural properties, even if not the shortest route. This distinction means breadth first search is ideal for navigation and finding optimal routes, while depth first search excels in tasks like topological sorting, cycle detection, or exploring game trees. Understanding their core mechanisms helps you choose the right tool for the right problem. So why does this matter? Let's look at 3 real-world problems that graphs solve every day. First, finding if two people are connected in a social network, like LinkedIn's degrees of separation. You start at one user and run BFS, spreading outward level by level until you find the target. BFS guarantees the shortest connection path. Second, detecting cycles, like finding a loop in a friend group. You run DFS, and if you encounter a node you've already visited, you've found a cycle. DFS is perfect for this, because it explores deeply and tracks the path. Third, recommending friends. You run BFS from a user's direct friends to find friends of friends, then filter for mutual connections. This is how LinkedIn suggests people you might know. Every one of these problems, navigation, cycle detection, and recommendations, relies on graph traversal. Master BFS and DFS, and you unlock the foundation for solving complex connectivity, routing, and recommendation problems across every domain. That's the power of graphs.